Then in a wireless charging system, we can install automatic aligning system to charge the batteries. And when we are moving from static wireless charging to quasi-dynamic wireless charging system or dynamic wireless charging system, we can also reduce the bulk battery requirement. That is, charging our vehicle for a certain period, we can charge the vehicle intermittently so that we can reduce the requirement of energy storage system, and also we can charge our battery intermittently. By that, we can extend the driving ranges of our vehicle, because based on battery only, the companies are specifying the driving ranges. If you charge your vehicle one time, the vehicle will cover this distance. Okay. So when we are going to dynamic wireless charging system, we can extend the driving ranges of our vehicles. Then normally different type of wireless charging technologies are there, but in a EV charging system, they are majorly preferring inductive power transfer technology to charge the energy devices. See, by 2030, the greenhouse gas emissions will be increased by 14%, and all the governments insisted to reduce the greenhouse gas emissions because the temperature, the global temperature also increasing day by day. So for that, we should reduce the greenhouse gas emissions. Then this animation just representing how the wireless charging system works. Then these are all the basic wireless charging system. First one is static wireless charging system. When vehicle is positioned over the charging pad, it gets charged. Then the semi-dynamic or quasi-dynamic charging system means we will install the charging pad on a certain distance. When vehicle is moving over the charging coupler and positioning over the charging coupler, it will get charged. In Gumi City, this one university installed, Utah University installed this quasi-dynamic wireless charging system. Then third one is dynamic wireless charging system. In part of the road, we will install this wireless charging track. Whenever the vehicle need to charge, the vehicle can travel over the charging track, and the energy storage system of the vehicle will be energized by this charging track. Then, so when we are discussing about charging couplers, the charging couplers are the heart of the wireless charging system, because the charging coupler only going to transfer the energy from transmitter side to receiver side. Here, the air is acting as a core medium. Already, all of you studied about the working principle of transformer. In a transformer, the common core will be there. Here, the air medium is acting as a core, and it is a loosely coupled system. It is not a tightly coupled system. It is a loosely coupled system. Then the conducting material, the selection of conducting material is also a major role in a design of charging couplers. The factors involving in the charging coupler design is, first, we have to finalize the power rating. At what power we are going to design the charging coupler. Next, at what distance we are going to transmit the power. Then, based on the rated power level and based on the transmitting distance, we have to calculate the coefficient of coupling, mutual inductance between the charging coupler, and self-inductance of the charging pad, and the quality factor of the charging pad. Next, interoperability. Interoperability, it is nothing but the user friendly. The charging coupler should be user friendly. Whatever the transmitting pad we are installing under the ground, that how to transmit the power irrespective of the receiver type. That is the interoperability. Nowadays, the researchers are concentrating on this interoperability and cost. Already, due to reduce the cost of the electric vehicle, we are going to the wireless charging system. So we have to concentrate on the cost, because whenever considering the price of an electric vehicle, the batteries are contributing more cost compared with other system. So we have to analyze the cost of the infrastructure system. Next, misalignment tolerance. Misalignment tolerance is nothing but we want to assure that the coils, the transmitter pad and the receiver pad is always in aligned condition. Sometimes it will in the misaligned condition. So whatever, irrespective of the misalignment condition, we have to transfer the maximum power. So that also we have to analyze whenever we are designing the charging coupler. Next, heat dissipation. We are going to install the transmitter pad under the ground, and also we are going to design the receiver pad under the vehicle. So we have to check whether the coil, the air is circulating properly in the charging coupler. That's it. So these are all the factors of the charging coupler. Whenever we are considering the charging track, there are two different type of charging track. One is continuous charging track, another one is a segmental charging track. In a continuous charging track, the control is simple because only one converter we are going to use to energize that track. In a high power system, they are installing this track, but the continuous energy process should be there. Due to this continuous energy process, major part of the energization will considering as a loss, because some part of the coil only covering by the electric vehicle, but remaining part are considering as a losses. So for that only we are preferring segmental analysis, segmental charging coupler. So for that only we are considering segmented charging coupler. In a segmented charging coupler, we can reduce the losses of the charging coupler, because by using proper driving circuit, we can energize the particular charging coupler. The remaining charging coupler, we shouldn't energize. We can turn off that charging couplers. Next, these are all the major parts of the charging coupler. First one is coil. Second one is the tray that is required whenever you are seeing the charging pad in an induction stove. They are lodging the conductor in a particular spacing. So that is a coil former. Next, ferrite core, then aluminum ring. These we will discuss about these are all the what is the requirement of these parts in a upcoming slides. Then top of that plastic cover to cover the charging coupler. So these are the types of charging coupler. In a wireless charging system, we have to consider two parts. The one is a transmitter, another one is receiver. So in a types of charging coupler, there are two different types based on the flux position. One is non-polarized, another one is polarized. Non-polarized, just see the diagram. Non-polarized means there is no form of magnetic poles on the coil. There is no form of north pole and south pole. Always the charging coupler producing the vertical flux. There is no possibility of horizontal flux, and also there is no possibility of forming magnetic poles. There is north pole and south pole. But when you are considering the polarized structure, the north pole, south pole, here if it is forming the north pole, here it may form south pole. The north pole and south pole will form in a polarized structure. Then the basic charging coupler in a non-polarized is circular, rectangular, square, and hexagonal. The circular is maximum they are preferring in circular and rectangular, they are maximum preferring in stationary wireless charging system. And in a polarized structure, the double D coil, double D quadrature, and the bipolar and tripolar. This diagram is representing a double D structure, and this diagram representing double D quadrature. Just we are placing the quadrature coil on the double D coil to extract the maximum fluxes. Whenever we are designing the receiver pad, what is the need of receiver pad? It should extract maximum flux from the transmitter pad. What is the need of transmitter pad? It should transmit the maximum flux to the receiver pad. That's it. So, and bipolar pad is by reducing the copper turns compared with the DDQ coil. Compared with the DDQ coil, the bipolar coil is using less amount of copper and it will extract maximum fluxes. And tripolar coil, the ORNL, the Oak Ridge National Laboratory, developed this tripolar coil for a 200 kilowatt wireless charging system. It is normally used in a three-phase system. Then, when we are usability, I said the circular pad and rectangular pad they are using in stationary charging system, and this DD pad we can prefer in a transmitter side because we are going to energize the DD pad with a single unit, a single power converter unit. But to energize this DDQ pad and this bipolar pad, we are requiring two different power converters. So for that only, we can prefer this DD pad in a transmitter side and DDQ receiver pad we will consider in receiver side. By that, we can use two rectifier unit to do the energy conversion. That's so here there are two different coil structures. One is a loop coil, another one is a dipole coil. So loop coil is nothing but the coil structure is a planar type, and the dipole coil is nothing but the coil is wounded and a ferrite bar. So the advantages of the loop coil is it will generate a minimum EMF and the size of the pad is compact, but it offers lateral misalignment tolerance, minimum lateral misalignment tolerance. And considering dipolar coil, even though it is offering high lateral tolerance and high coupling factor, the EMF emission, we have to consider the ICNIRP is fixed some standard, that is the magnetic field strength and electric field strength around the coil within this limit. In yesterday class, sir discussed about that. And so we have to consider that the limits also. When you are using a dipole coil, it will emit the huge EMF. Then when we are considering a core, with the core, without core, when you are considering the core, the coupling factor of the charging coupler will increase and the leakage flux also reduced. And without core, the Q factor is increasing, and the core we can reduce the core loss because the core is contributing the core loss additionally to the charging coupler. When we are not using core, we can reduce the core loss, but the EMF emission is there, magnetic leakage will be there. Then when you are using dense core and when you are using sparse core, normally in an induction stove also they are using a sparse core only. When you are using dense core, we can easily install, because whenever you are purchasing a core, the standard shapes are there. When we are moving to cut the core, ferrite core, the cost of is not affordable. Cost is not that much affordable. So only the people are using standard size core. So when you are using dense core, the core structure is not optimized. But when you are using sparse core, we can optimize the core structure. Then in between the gap, the EMF leakage will be there. When we are preferring the shield, when we are we can use two different type of shielding methods. That is, one is a ferrite itself we can use as a shield, and aluminum as a shield. That is, when we are using conducting medium as a shield, when we are using magnetic medium as a shield. When we are using magnetic medium as a shield, for an example ferrite, we can mitigate the magnetic flux, and we can reduce the losses by using additional aluminum shield, but the power loss is increasing. But when you are using metal shield, it is very effective for high frequency system, because the charging frequency of our wireless charging system is 85 kilohertz. Then the power loss will be happened. Then the addition of core is increasing the inductance. When you are adding the shield, that is, when you are adding aluminum shield to the charging coupler, the value of inductance will be reduced. Then these are all the basic pad structure: circular pad, square pad, octagonal pad, and hexagonal pad. Then in this, you should always concentrate on a spacing and width of the conductor. The spacing of the conductor should always lesser than width of the conductor. Then D in is nothing but inner dia of the charging pad, and D out is nothing but outer dia of the charging pad. Some basic formulas are there to calculate the inductance of these charging pads. The first one is modified Wheeler formula. Then these are all the methods are used to predict the inductance. Even though we are predicting the inductance by using this formula, it won't give the accurate results. Maybe the 10% or 15% deficiency will be there. Then, so it is a modified Wheeler formula. Here, K1 and K2 is a constant. For that, if we are considering a square, we can use a 2.34 as a K1 and a 2.75 as a K2. For circular, K1, K2 value, we have to consider as 1. And N square is nothing but number of turns. And rho is a fill ratio, which is the ratio of difference and addition of the dia, inner dia and outer dia of the charging pad. Then it is a current sheet approximation. In the current sheet approximation, it exhibits a maximum error of 8% for when the spacing of the conductor is lesser than equal to 3 times of the width of the conductor. Then just to see this condition, you should always concentrate on this condition. In a practical consideration, the space between the turns should always lesser than equal to width of the conductor. Then the charging coupler, we have to wound tightly, because when you are wounding the charging coupler tightly, the magnetic coupling is in effective. If you are allowing spacing between the increasing the spacing between the number of turns, the charging coupling between the transmitter pad and the receiver pad is not that much effective. Then it is a monomial expression. You can find the inductance of the charging pad using these expressions. Then wire selection. Then because we are transmitting the power in a high frequency, because already you know the reactance of the inductor is 2 pi FL. Just we are reducing the L value, we are reducing the inductance of the charging pad and increasing the frequency value, so that we are matching the inductive reactance value. Here already we studied in a transmission and distribution, to reduce the skin effect, we have to go for standard conductors from the solid conductors. So here we are using Litz wire in a design of charging coupler. Here the number of strands we have to select whenever we are approaching the supplier. Sir, we want to purchase a Litz wire. They will ask, sir, what is the number of strands you are acquiring? So first we have to decide the number of strands. So number of strands will give by this expression area of cross section of overall wire and area of cross section of each strand. First, the area of cross section of each strand will given by this table. Here, the standards are there for 20 to 50 kilohertz. The AWG, that is American wire gauge, they are preferring 36 AWG, and the bar wire diameter is 0.127. And because some Chinese researcher initially they transmitted the power in 20 kilohertz. But when they are transmitting the power in 20 kilohertz, the inductance of the charging pad is high. Then now the SAE developed the charging stands and transmitting the power in 85 kilohertz. So to transmit the power in 85 kilohertz, the American wire gauge is 38 and the diameter of the charging stand is 0.102. Then number of strands twisting. It is not a sink depth, it is a skin depth. Okay. So here the number of strands twisting is can found by 4 into skin depth whole square divided by diameter of the single strand square. Because why we need to consider this skin depth? Because the diameter of the selected strand should always lesser than skin depth. Here the rho mu or the constant parameter, that is the conductivity of the copper. If you are using copper wire, conductivity of the copper and the permeability of the copper, F is the operating frequency. Then to design the to select the leads wire for a good design, the stand diameter always smaller than 4 times of the skin depth. Then the current rating, if you want to, the number of strands also preferred for a current rating. If you want to 10 ampere or 20 ampere, we have to select a particular current range. Here they are preferring the current rate. For 38 AWG, the maximum current allowed by the individual stand is 0.0228. If we are considering a 36 AWG, the maximum current rating is 0.035. Normally, the American wire gauge system also we can follow, and the standard wire gauge system also follow, that is SWG. SWG, we can prefer 42 SWG for this 85 kilohertz system. When you are considering AWG for 50 to 100 kilohertz, we can prefer 38 AWG. When the suppliers are considering SWG for 85 kilohertz system, we have to select 42 AWG. Irrespective of SWG and AWG, based on skin depth also, we can select the wire diameter. Then when we are entering into the FEA analysis, normally we can design or we can calculate the self-inductance of the charging pad and mutual inductance of the charging pad. But we can't finalize the distance. We can't finalize the distance between the charging pad because it is a non-linear parameters. All are non-linear parameters. For these, there is no standard relationship between distance and the coefficient of coupling. So to optimize the distance between the charging pad and to optimize the mutual inductance, to optimize the Farad structure, because already I said addition of Farad increasing your charging pad inductance and addition of shielding, aluminum shielding, reducing your charging inductance. So you should optimize the charging pad parameters. The majorly we have to consider 5 parameters. One is self-inductance of transmitter pad, self-inductance of receiver pad, then coefficient of coupling, then mutual inductance, then quality factor of the charging. Already all these parameters we might study it in basic circuit analysis and electromagnetic analysis. So these 5 parameters only deciding the power transfer efficiency. See, the ANSYS Maxwell, different softwares are there. COMSOL, ANSYS Maxwell, different softwares are there. Here we are preferring ANSYS Maxwell 3-dimensional analysis. In this ANSYS-Maxwell three-dimensional analysis, there are different solution type. One is magnetostatic, another one is eddy current, another one is transient. Magnetostatic is nothing but just whenever we are using solid conductors, we can prefer magnetostatic. And when we need to give phase angle, when we need to fix frequency of excitation frequency to the charging pad, we have to prefer eddy current. The transient is preferring when moving parts are there, electromechanical parts are there, we can prefer transient. The electric, when we are preferring inductive power transfer system, we have to go for this magnetic analysis. And when we are preferring capacitive wireless power transfer system, we have to prefer this electric. In this electric solution type only, we can do we can prefer electrostatic, DC conduction, and electric transient. Then, so it is the front window of the ANSYS electronic desktop. In this ANSYS electronic desktop, we are going to design our charging coupler in Maxwell 3D. Even though the system requirement of this ANSYS Maxwell is 8 GB RAM, for our user friendly, for our comfortable view, comfortable projection view, we have to prefer this Maxwell 3D, because Maxwell 2D, we have to calculate the projections, because only two axis only we can view in a Maxwell 2D. So for a Z, for inward and outward projections, we have to virtually see the sections of the charging pad. So we have to prefer the Maxwell 3D design in this FEA analysis. Then when you are opening the windows, when you are opening the ANSYS Maxwell window, the property window is representing the parameters. If you want to do sweep analysis, if you want to sweep the frequency from 50 kilohertz to 100 kilohertz, if you allow the excitation current from 1 ampere to 10 ampere, or if you want to move your charging coupler from minus 150 mm to plus 150 mm horizontally, you have to set the variable. So you can change the variables from this property window. Then this progress window shows whenever you are simulating your charging pad, this progress window shows the percentage completion. Then this message manager, once the simulation started or once the simulation completed, the message manager, or we can view the error also. If the error shows the error, it will show the error also. Then project manager, in a project manager only, the step-by-step process they mentioned. That is, first we have to assign the boundaries, then we can give the excitation, then we have to set the parameters, then we have to set the meshes. Okay, because on the surface of the object, we have to set the meshes, required meshes. Then in an analysis, the percentage of error, whether we need to run the simulation in an iterative method or non-iterative method, in the analysis window only we have to fix. Then in Optimetrics, if we set the parameters, we can set the sweep settings in a Optimetrics window. Then in the results, we can see all the results. Then just to see, I simulated a basic circular coil system. I drawn the region, okay, because it is a air medium. Without the region, it automatically selected the vacuum. So just we are considering the air region. For that, I drawn one box. In a model window only, whatever we are drawing in a model window only, it is showing the different type of objects. Then I drawn receiver shield and TX shield, and I drawn RX coil, that is a receiver coil and transmitter coil, and I drawn RX core, receiver core, and transmitter core. So whatever the object you are drawing on this window, all will show in this under the model section. Then here I just excited the receiver coil and the transmitter coil, and in a parameters we can obtain the matrix. Then in a mesh settings, each and every element we have to set the mesh, and in a setup we can set the solver type. And in Optimetrics, here I didn't prefer any variables. Okay, for current I just fixed 10 ampere. For a frequency I just fixed 85 kilohertz. For a distance also I just kept 100 mm. So for that, in this design there is no need of parametric sweep, so I didn't prefer Optimetrics. In a result section we can take inductance, coefficient of coupling, mutual inductance, and we can measure core loss also. Just to see the time taken whenever you are drawing a complex structure, the time taken to simulate the coil structure is high. So I just simulated this coil. The simulation starts at 5:04 p.m. and the simulation starts in 5:90. That simulation, it is just it taken 15 minutes. Okay, so based on the complex design only, the simulation will run. So how to draw the charging couplers? Directly we can go into the ANSYS Maxwell software. So it is the ANSYS Maxwell software. It is a desktop. Here you have to click Maxwell, and we are going to draw ANSYS Maxwell 3D design. So just I'm clicking on ANSYS Maxwell 3D design. So just to see, when you are clicking on ANSYS Maxwell, the solution type it is showing. Defaultly, it will show the magnetostatic. To change the magnetostatic into eddy current, you have to click Maxwell 3D and the solution type. Here, you may change this solution type from magnetostatic to eddy current. Already I said the difference between magnetostatic and eddy current means in a magnetostatic, we can't set the phase angle. Already I said by the different type of charging pad structure, DDQ bipolar coil. In the double D quadrature coil, the flux between DD pad and that quadrature pad must be decoupled. For that, the phase angle of the current should be different. Okay, so the flux should cancel each other. For that, we have to offer a phase angle. So for that application, we can prefer eddy current. So here the default is magnetostatic. Then to draw the standard coil structure, if you are preferring, I want to draw the square coil. So you have to click on draw, then grid settings. In a grid settings, in a practical applications, the diameter of the lead wire is standard. So based on the diameter, we can fix the grid settings. So for that, view grid settings. In a grid settings, there are options of the grid visibility, show, hide, auto. If you click the show, it will fix the size. When you are fixing the auto, based on your scrolling, it will show the grid system. And when you are disabling this auto adjust density, then we can fix a Cartesian, that is the changes of in x-axis, changes in y-axis, changes in z-axis. If my conductor size is the conductor dia is 4.2 mm, I have to give here, for an example, 4 mm. So I have to give here dx is 4 mm, dy is 4 mm, and dz is 4 mm. So if I am giving like this, the grid, just to see here, the grid is, so orient top angle, and I'm clicking 1 because here it is in 3 mm. Already I said the grid settings is 4 mm. So I'm scrolling out. I'm viewing the grid. I'm viewing the grid. Okay. So in a grid system, view, grid settings, I'm just clicking on auto. So that whenever you are clicking on line, it will show the grid on a window. Just to see in a right side, measure data. It will show X distance, Y distance, Z distance. So when I want to draw the line in minus x-axis for 10 mm, you have to click here and you have to move along minus x-axis just to see the window, the right side measure data showing X distance is 55 mm. And when you are moving in plus Y direction, so the Y is showing minus 70 mm and X value is showing 0 mm. So the line is straight and we are moving only Y distance, and we can move in positive X side and only the positive X is changing. And when we are moving in minus Y direction, the Y is changing in positive. Okay. So like this, we have to draw the whatever the coil. If you want to draw the square coil, if you want to draw the rectangular coil, you have to draw like this, because in a predefined structure, we can draw a helix, segmented helix coil with the rectangular shaped conductor and circular shaped conductor. So just to see here in a draw, I'm just clicking user defined primitive in segmented helix and polygon helix. Rectangular helix also there, but the conductor shape is a rectangular. Here in the polygon helix, we are going to draw the polygon helix, because in when we are handling electromagnetic theory, in that magnetic field of the solenoid coil, magnetic field of the toroidal coil, for all the topics, just we derived the equations. But when we are using this Francis Maxwell for a research purpose also we can use, for teaching purpose also we can effectively utilize this software. So just to see here, the parameters, just I click to draw and examples and segmented helix. So the parameter user defined primitive parameters are there. The polygon segments representing how many phases are there in a conductor. How many phases are there in a conductor? If you are using rectangular conductor, in an antenna, we are using rectangular conductor, isn't it? So when we are preferring the smaller power application like antennas, we can drawing the rectangular shaped conductor, but the normal electrical wire is in circular manner. So we have to change these polygon segments from 4 to 0. 4 to 0. Then polygon radius, that is polygon radius is nothing but outer radius of the cross-section polygon. That is, we are fixing the radius of the conductor. So last time I'm fixing 2 mm. So 2 mm is nothing but the diameter of the conductor is 4 mm. Then start helix radius, that is the distance of the distance between center of the conductor to origin of the medium. So just I'm fixing it is 20 mm. 20 mm. Then radius change. That's what we discussed in a slides. The radius change should always greater than 2 times of the polygon radius. 2 times of the polygon radius, because 2 times means the polygon radius is 2 mm, means the polygon diameter is 4 mm. So it should greater than 4 mm. So the radius change is I am giving as 4.1 mm. Then pitch. If we want to draw the helical coil, just I'm giving for an example. I'm not drawing a planar coil. For an example, I'm just want to show you how can we draw the helical coil. Just I'm giving the pitch value, that the distance between first turn and second turn. Okay, just I'm giving 1 mm, and the number of turns I'm giving 3 mm. Sorry, 3 turns. Number of turns is 3 mm. Just I'm clicking on OK. Just to show, due to that 1 mm only, it is showing like this. I'm increasing 5. front. Okay, so just due to the, I gave radius change also. For radius, by giving that radius change only, the coil is looking like. If I change the radius change is 0. Just see. The coil looks like this. Okay, if you want to draw the core, just I'm orient, I fixed the top. If you want to draw the core, you have to click on this. That's it. We have to draw the box. You may draw the core. You may draw the core. Okay, you may project it, and just to orient, you have to click on the box. The Z size I am fixing as 20 mm. The X size and the Y size is fixed. Just I am click on this. Just to see, I'm changing the color of the polygon helix. We can change the color of the object and the materials of the object. Just to see, I clicked on this polygon helix. Just to see the name itself is showing polygon helix. We can rename it. That is a coil, and we can assign the material. I just double clicked on that polygon helix. We can assign the material. Just I clicked on that material. You have to click on this line. Sorry. Here. Edit. Okay, material, edit. When you are clicking on edit option, we can assign any material, aluminum, okay, or otherwise iron, cast iron or iron, otherwise copper. Okay, so copper we can assign for a material. Then we can edit the parameters of the material. Just we have to click on view or edit material because it is predefined. Okay. Right. Okay. Okay. Already it is defined. Already I did in project. So copper. That is, I have to select the copper. Edit. Copper already I am using in a project. So only view or edit. Okay, view or edit. See, here we can change the relative permeability, bulk conductivity, magnetic coercivity, and magnetostriction, inverse magnetostriction. All the parameters we can change. Just see here, due to you selected the magnetostatic, here it is not showing the stance selection. You have to change the solution type, or you can view the number of stance preference here. So I just assign the copper for material, and by double clicking on this, we can change the color also. I am just clicking on this. I change the color. Okay. Then here also the box I am telling as a considering core. Already ferrite is there. So just I am considering, I am changing the color of the object into gray, and okay. I changed. Okay, that's it. So if you want to draw the planar spiral coil, again draw line, user defined primitive segmental helix, polygon helix. Here, the polygon segment. Just I'm clicking on 4 just to see the coil structure. Polygon helix. I'm just hiding this one. I'm just see the polygon segment is, when polygon segment is 4, just to see the conductor is rectangle. The conductor is in rectangular shape. Okay, so for that only, just I'm deleting this. I'm deleting this. We can click on delete. Okay, then we can give coil. Still, for coil, the parameter is not assigned, so that I'm clicking on copper. Sorry, maybe it is user defined primitive. Already I opened the one completed design, so it is like that. Then here the excitation, when the conductor, okay, when you studied on the boundary conditions, when you are giving the excitation to the conductor, the tip of the edge of the conductor should always in on the boundary side. So for that, just I'm moving to draw the line. I'm just zooming in and clicking on F. I just clicked on this. So I'm going to draw the additional line to give the excitation, because when you are drawing the region, the edge of the conductor should touch the boundary of the region. So for that, I'm just clicking on the line and just see, when I'm moving, it is not showing the circular line, but when I'm moving at the center of the conductor, it is showing circular. Are you getting my point? When I'm moving somewhere of the conductor, it is not showing circular line. When I'm moving center of the conductor, it is showing circular line. So just virtually you have to think 3 lines. One is outward projected, one is topward projected, another one is towards the axis. So just I completed the line and fit all. Okay. So first here it is showing line. For that, create a polyline, first line, first. Okay. You have to, you just set in front view. You just set the front view. So that only the axes are there, Z axis, Y axis. So first line, you should extend towards the positive Y. So just I'm copying and pasting the same parameter, and you want to extend the plus Y. So I'm just extending the line for 10 mm. Just a click. The line is extended. Then I want to move the conductor in Z direction. So just I am copying and pasting, and it is already, it is in 15 mm. I want to project towards positive Z. So I'm increasing again by 10 mm. So it is a 25 mm. So the line is projected. Then towards us means which direction? By clicking on orient, we can see positive X. So positive X, towards a positive X, we have to project. So control, when I'm pasting the same point, I have to project in positive side, positive X side. So I'm just increasing 19 mm into 30 mm. So see, the lines were drawn. Then I'm changing. I'm just double click on the create polyline. I change the type of the line into circle. Type of the line into circle. Okay. So then the diameter of the conductor also. The diameter of the conductor also changed. We can change the diameter for 2 mm. Okay, just see here. Okay, so like this only, we have to draw the additional line and front portion, and here excitation is there. Next, after here also you have to draw the line like this, and to give the excitation, press F, click on this edge, right click on this, and assign excitation. Voltage means you have to give in junction of the conductor. Current means you have to give facing of the conductor. Permanent magnetic field and all comes for, what is that? Any rotating medium or moving medium is there. Okay, so current, in a current excitation, we have to assign the current. We can fix the conductor as a solid conductor or standard conductor. We can give the value for 1 ampere or 2 ampere. In terms of kiloampere, we can give the excitation. And in a excitation, that's it. In a parameter, if you just see, I'm clicking on this, right click on this, excitation, current, I'm giving 1 ampere. Okay, 1 ampere I gave. Okay, so under the excitation is showing current. Then in orient, I'm just clicking on current on, it is showing towards the conductor. If I want to change the direction of current, because one end of the conductor, the current will enter, another end of the conductor, the current will leave. So I'm just a swap direction. The direction is changed. So I completed the excitation. Then in the parameters, assign force torque matrix. Here we want to see the matrix. Force torque and all in a rotational medium we can obtain in a matrix, because I didn't merge here. Okay, I have to merge coil and the polyline. Here, unite option is there. Okay, so unite option is in top of this. I have to unite that. Okay, that's it. So based on that, we can set the parameters. And the mesh also, for this, we have to set the mesh. Assign the mesh operation on selection and inside selection. On selection means for conductors, for core, for aluminum shielding, we have to click on selection. It is two different type, length based, skin depth based. Length based means the in terms of mm, just to see the 10 mm is there. The mesh means on the surface how the elements are finited. Like that we have to fix. Basically, to run the simulation fastly, we are giving 70%, 80% like that. But here I'm fixing. Now initially we have to reduce the mesh sizes 10%, 20% if you are having well conditioned system. Okay, that's it. Then inside selection means for boundary conditions you have to see you have to click on inside selections. Then analysis, in the analysis only you have to set the parameters, that is add solution setup. Just see here, add solution setup. So in a general, maximum number of pass per percent error. In a convergence, minimum number of passes, minimum converged passes. In a solver, you can enable the iterative solver. We can enable the number of nonlinear iterations, and we can enable the smooth BH curve. And when we are enabling the iterative solver, the time taken to simulate the oil structure is increased. Then save defaults. Then here, if we change the solution type into eddy current, we can fix the frequency here. That's it. So just I want to show the results produced by previous simulations. So this coil structure I drawn. So I gave just to see the model in a solids, air medium, region, aluminum, RX shield, TX shield, in a copper, RX coil, TX coil, in a ferrite, I just drawn RX core and TX core. Okay, that's it. I simulated just to see excitation current. I excited TX in, TX out, RX in, RX out. Then in a parametric, in a matrix, just to see when you are giving excitation in a parametric, that parameter will show. So you have to enable that. And in a mesh setting, for each and every element, each and every component, for region, for shielding, for coil, for core, you have to fix the mesh analysis. In the analysis, just to see the setup. I did in eddy current. So here frequency sweep solver will be there. I set 85 kilohertz. Okay. Then in optimetrics, I didn't fix the parameter. So the optimetrics block is not enabled. In a results, I just obtained inductance of the coil. Inductance of the coil. The inductance of the receiver pad is 9.87 microhenry. The mutual inductance, that is the inductance between TX and RX, is 1.73 microhenry. The inductance of the transmitter pad is 9.82 microhenry. Then we can calculate resistance also. Resistance of the wire used. See the resistance of the receiver pad, 10 milliohm. The reluctance, that is the resistance between transmitter pad and receiver pad. Reluctance, that is a 3.4 milliohm. The transmitter pad is inductance is 12 ohm. Then Z also we can obtain. That is the impedance of the charging pad. Then magnetic flux, pi also we can get. Just to see here, 17 microweber and 98 microweber by transmitter coil. Then coupling coefficient also we can obtain. So these are all the parameters we can obtain through the results. Just to see the results, right click on this and whatever it is, eddy current report or magnetostatic report, just a data table. Coupling coefficient, inductance, nominal inductance, resistance, nominal resistance, impedance, nominal impedance, magnetic flux, and losses, core loss, solid loss, standard loss, AC standard loss also we can obtain from this. Then we can view the flux region. We can view the flux region. I just see here, I will fix the front view. I drawn one sheet, one rectangular sheet by clicking here. I drawn one rectangular sheet, and by right clicking this rectangular sheet, here field is there, H, B, J we can obtain. From the B, magnetic B, vector B, that is magnetic distribution, and magnetic path we can click. So just I am clicking on this magnetic B. See, we can see the how the magnetic field distribution is there and how the magnetic flux direction is there due to shielding. Just in the bottom of the coil, due to shielding, there is no flux passage. So we can effectively teach our student by these software, FEA analysis software, how the flux is passing, how the flux direction, how could we view the current based on the current direction, how the flux direction is changes, like that we can teach. And for research parameter also, we can easily obtain how the, for particular distance, what is the value of M, for particular distance, what is the value of L. Okay, so that's it. From the FEA analysis software, we can obtain. Then, if in upcoming of what is that? We can, by these results, we can simulate a circuit that is ANSYS Simplorer. By using ANSYS Simplorer software, okay, by using Pin Builder, we can draw the circuit and we can simulate with these results, we can simulate the equivalent circuit. Okay, we can use that also. That's it. Thank you. If you are having any questions, just ask me. These are all the slides I kept for a basic operations. I will share the slide with the sir and he will forward that. So these are all the initial mesh setting. That's a length based, skin depth based, and in an analysis, and what are the results we can obtain. Thank you.
Thank you, Raja, for the nice presentation. Thank you very much. Participant, if you have any questions, you can raise. And you covered the basic modeling. Again, if you are going for a specific coil structures, we need to work on it. So hope this will be like giving a basic intro to the ANSYS Maxwell software. So participant, if you have any questions, you can post it in the chat or you can unmute yourself and you can ask. And there is one question, how frequency range is given to the coil?
Yeah, the frequency range already I told the solution setup. The solution setup itself, you have to select eddy current solver. When you are selecting an eddy current solver, in that analysis, you can view the frequency. Okay, with that, you can fix the frequency from 85 kilohertz or by using frequency sweep. I just shown a magnetostatic. You have to change the solution type from magnetostatic to eddy current solver. With that, you can assign the frequency.
And the next question is, how can I analyze the misalignment between coils?
Yeah, to analyze the misalignment, here what is the problem means, if we have to move the coil, because when the receiver pad with the coil, ferrite and the aluminum plate, we can't move both structure parallelly. So when you are considering coil alone, when you are moving the coil, we can, the input might be given as a parameter. By giving as a parameter in a property window, in a, what is it, in an optometric, you can sweep that distance also.
And the third one is how to get the simulation results.
Yeah,
Means how to
on the
see the
result is there, no, that the tree is there in a progress of the tree is there. You have to right click on that result, then eddy current report or magnetostatic report. With that, you have to get the data table. So with that data table only, we can get different parameters, and to see view the magnetic field intensity and magnetic flux density, you have to draw the plane, okay, vertical plane or horizontal plane. By clicking on that plane, you can view the magnetic field intensity and magnetic flux density distribution.
Yeah, so I think if you have any more questions, you can write to us, and we'll happy to address all this. And with the various shape that is DD and DDQ pad also we can able to design using ANSYS Maxwell. And if you are particular about that, you can reach to us. We can help you on that. Thank you very much, Yuvraj, for the wonderful session. Moving forward, I now request the next speaker of the today's session, Mr. Rahul Kumar. Rahul, are you there on the line?
Yes, sir. Am I audible?
Yeah, audible. You can share your screen.
Thank you, sir.
Yes. The next speaker for today's session is Mr. J. Rahul Kumar. He is a junior research fellow for the core research grant project and a research scholar in Department of Electrical and Electronics Engineering, SRM Institute of Science and Technology. He has more than 6 years of teaching experience, and he's also worked in various projects related to the wireless charging and then electric vehicle applications. He is good in wireless charging system design. He is good at wireless charging system design, both in the simulation as well as in the practical. He has a good experience in the practical aspect also. And he has published various papers related to the wireless power transfer system in reputed journals. And he is having a real time simulation exposure in especially on the MATLAB interface, for example, using the OpenRT platform. And I now request Rahul Kumar to take over the design aspects of wireless charging system. So he will be covering about how to calculate the power rating of each and every element which is there in the wireless charger, and also will be covering about the MATLAB simulation model for the wireless charging system. Over to you, Rahul Kumar.
Very good morning, sir. Am I audible?
Yes, you are audible.
Okay, thank you, sir. Thank you for the session. Dear participants, very good morning to one and all present here. We are in the day 4 session. I hope you are enjoying the session. In the day 4, section 2 is asked. Our topic is wireless power transfer system analysis using MATLAB. It's presented by me. It's correlating with ANSYS Maxwell and MATLAB. So let's see what we are going to do with MATLAB. So how far that MATLAB will help us to analyze the wireless power transfer system in a simulation analysis. So first of all, let me start with wireless power transfer block diagram. We all came across several sessions about wireless power transfer system. In a wireless power transfer system, we can classify basically the block diagram into primary transmitter unit, secondary receiver unit, then intermediate magnetic coupling unit. Okay, here the generalized block diagram, I can classify the entire system into three blocks. The primary unit is supply the power from a grid or any energy sources to the intermediate wireless region. This wireless region is an contactless medium. Here, the inductive coil is preferred for our wireless power transfer system in a system design. This coupling region contains primary transmitter coil and secondary receiver coil. Along with that, the receiver pickup coil receives the power from the transmitter coil, and the received power is sent to the EV load. So this is what the wireless power transfer system works for EV application. Here, the functional block diagram of the WRIPT system. WRIPT system is the science wireless resonant inductive power transfer system. As I said you before, we have primary power modulator unit, which is an outboard unit. Outboard unit is present in a stationary unit, but onboard unit, which is present inside the vehicle. Our transmitter coils are embedded in the roadways or in the surface of the ground level. So the conducting medium for our wireless system is the air medium, which is present between our ground level coil and the vehicle mounted receiver coil. So here, in previous slide, I have classified our system into the three models. One is primary transmitter model, secondary receiver unit, then intermediate coupling unit. So this primary transmitter model and secondary receiver model are generally decoupled, generally coupled through air medium, which is nothing but a contactless region. So while simulating, we can go with two varieties of simulation. One is electromagnetic analysis, another one is power transfer analysis. In a power transfer analysis, we can simulate the entire system, entire three blocks, which consist of electromagnetic performance, also and power switches for a conductive analysis. So in a primary transmitter unit, which is kept in a outboard unit, which takes the power from a grid or from renewable energy sources or any other power sources, then the taken power is converted to the high frequency AC power to supply towards the receiver coil. How it happens? It happens through this block. Here, our block consists of the grid. Then grid power is an AC power, which is low frequency AC power. It's converted to the DC power using AC to DC converter, which is our normal rectifier. Then the DC input is given to the high frequency AC power modulator, which is inverter. This inverter is controlled through the high frequency pulse. This high frequency pulse is output of the inverter is given to the coil through the primary compensator unit. This primary compensator unit helps us to stabilize the power transients during misalignments or during minor misalignments or during any other minor changes in between the misalignment conditions. So this is about the primary power modulation unit, which is outboard unit. This is entirely separated through air medium in the intermediate wireless medium. So here, vehicle is aligned over the primary coil. The secondary coil is directly coupled over the primary coil. The aligned coil of receiver unit is given to the secondary compensation network. This compensation network compensate the balance the resonance of our receiver coil with respect to our transmitting power to maximize the efficiency of power transfer in a magnetic coupling region. This received pickup power is compensated in the secondary unit. Then the secondary compensation, then it is given to the AC to DC conversion, which is our high frequency AC power to the DC magnitude. Then it leads to the battery bank or energy storage unit. This is about our system block diagram. So here in a primary unit, secondary unit, and intermediate wireless coupling unit, we have different parameters. So when it starts with power source, then the conversion unit, we have in the primary side we have two stages of conversion. One is AC to DC conversion, then DC to high frequency AC conversion. Then the compensation unit. Then we have an intermediate wireless coupling region, which consists of primary transmitter coil and secondary receiver coil. In a secondary receiver power demodulation unit, the received power from the secondary receiver pad is compensated. Then it is converted the AC received magnitude to the DC magnitude. Then we, for efficiency enhancement purpose, we can go for chopper charge the battery efficiency. This is the overall block components of the WPT system. This is common for both static system, also for in motion, which is quasi-dynamic or dynamic system. So in analysis, we have two types of analysis. One is magnetic coupling analysis, another one is power transfer analysis. So magnetic coupling analysis, as we saw in a previous section by Raja sir, we discussed about magnetic coupling, which involves many number of geometrical coils for primary pad and receiver pad. So by coupling the both transmitter and receiver, we can transfer the power in an air medium. This can be analyzed using the magnetic coupling analysis. So another one is wireless power transfer system analysis, which is a combination of all the power conversion unit, and the power transfer analysis is the combination of magnetic block components. So to design and analyze the WPT system, in previous session we saw how to use ANSYS Maxwell. In ANSYS Maxwell, it's very easy, and it's very useful to simulate and analyze the electromagnetic performance. But in a MATLAB, we cannot design a coil, we cannot design a electromagnetic novel coils in a MATLAB. The feature is not available. So we have to go for ANSYS Maxwell. So this ANSYS Maxwell is best suited for electromagnetic analysis. Then we finally are concluded about ANSYS Implorer. ANSYS Implorer, we can design a power transfer circuit, but it's complicated to go with control pulses. We cannot generate our own control pulses like PWM or any other control actions. We cannot perform with the ANSYS Implorer. So control circuit is complicated in a Implorer, which is not possible. Generally, what people used to do, they used to have an ANSYS Maxwell design for electromagnetic simulation. Then they will go for ANSYS Implorer for designing a power electronics converter designs. Then for is that was now I am audible, sir? Now I am audible, sir? Okay, thank you, sir. Generally, people used to simulate using ANSYS Maxwell, then they will go for ANSYS Implorer, then MATLAB simulation. These three are co-simulated to analyze one system. But in a previous session, we understood that ANSYS Maxwell simulation is a time-taking process, also which we need a high-end PCs for simulating the system. So for a system analysis of electromagnetic, we can go for ANSYS Maxwell, then designing a control circuit and the power electronics converters. It's better to go with MATLAB option. So this is a simple and easy method for analyzing the WPT system that we are following. So in a MATLAB, in a ANSYS Maxwell, this is what we have seen. What they have did, they have analyzed the magnetic coupling, which deals with the eddy current simulation analysis. Here, we can draw the 3D geometry or a 3D geometry of our coil, like a circular or any other geometry. Then we can simulate the geometry to know the inductance and inductance parameter or magnetic parameters of our coil, our self-designed novel coils. So here, the outcome of the magnetic coupling analysis is self-inductance of our transmitter receiver pad, which is L1 and L2. We can take from here for using in a MATLAB. Then we can take the mutual inductance parameters, then resistance of the coils R1 and R2. So this is what the our ANSYS Maxwell will help us to come up with a power transfer analysis. So as I started discussing about magnetic coupling analysis, here you can see this is the single coil simulated in ANSYS Maxwell. When it is coupled, it is transferring power from the downside coil to the upside, which is transmitted to the receiver. This is how the performance will happen when this is for an ideal condition, which is circular to circular coil. We have many other geometries. We can go with any combinations for making wireless power transfer system. So here we know that we have a two-state of wireless power transfer system, which is static state and in-motion state. Whereas in-motion state we can claim it as the dynamic or dynamic state. In our previous literatures, we have taken some research study. What are the things happened in a wireless coupling architecture? The basic architecture is single transmitter coil to the single receiver coil, which we have primary of single transmitter pad and secondary of single receiver pad. In another combination, we can go for combined single coils to form a multiple combinations, like two circular coils or two rectangular coils, or a combined D structure to D structure, DD coil or DDQ coil. Like that, we can go for many other combinations to address the misalignment challenges. Here, interoperability is one of the parameters that we have to concentrate. It's a challenging parameter. So to address the misalignment challenges, we can go for like these combinations to make a system efficient in a power transfer. So here I have shown 3 different architectures, which is a single transmitter to single receiver, then double transmitter to single receiver, which can work in a static mode if a coil is receiver coil is aligned perfectly over the transmitter coil. Then it's okay. Our power transfer will happen to the maximum efficiency. When it is misaligned, then we may face the misalignment challenges. To address these, we can go for double coil in a transmitter and a single coil in a receiver, which can increase our power transfer efficiency in the wireless medium. So likewise, we can go for multiple combination of dual transmitter, dual receiver, multiple transmitter to single receiver, multiple transmitter to dual receiver, single transmitter to multiple receiver. These are the combinations for various power transfer systems that we discussed in our literature that you can refer. So now I come to power transfer analysis. Magnetic coupling analysis discussed in the previous session. This power transfer analysis is our part, which involves the development of primary transmitter unit, secondary receiver unit using power electronics switches with magnetic coupling parameters. Let's see how we are going to deal with 3 different blocks. So the goal of our system is to design an efficient, compact, reliable power electronics for high power operation. Is a challenging because power electronics is a challenging parameter for working with high current and high voltage, especially with high frequency. So we have to select the switches accordingly. That I discussed in yesterday's session. So in power transfer analysis using MATLAB, we can perform 2 different kind of analysis. One is Simulink design model. Another one is script coded model. We can work with coding to know to compare the plots or to analyze the efficiency and the frequency parameter or power parameter in a script window. For analyzing the system, with combination of multiple components like power conversion unit, then electromagnetic unit, then batteries. So these all the things can be performed using Simulink model. So Simulink model, we can do the analysis for a entire system in a script window. We can solve our own equivalent circuit. We can take some derivations for any parameters like mutual inductance or efficiency or coupling factors. Like that, we can take some derived equation for our system. Then we can simulate our formulas or equation in the script window to take the 2D curve. For example, mutual inductance versus efficiency, or power coupling factor versus efficiency, or power capacity versus resonance frequency. Like that, we can do many things with our script window. So here we are going to deal with the two things, which is script window, also in Simulink design. So before that, let me explain what we are going to design, then how we are going to start our design. So here, electrical circuit for WPT system with a series compensation. Okay, when I start the session, I have classified the entire system into 3 blocks. One is primary transmitter unit, another one is secondary receiver unit, and the intermediate wireless coupling medium. Okay, here our primary transmitter have the DC source, which is given to the high frequency power modulator, which converts the DC magnitude pulse to the high frequency output of the inverter. This is an AC pulse is given to the coil. So through our primary compensation, which is series compensation, series capacitor compensation. Likewise, we have some mutual inductance in between. It can be happen due to the coupling factor. When the coupling factor is getting varied, our mutual inductance parameter will get varied. So likewise, as per the law, our electrical laws, will receive the pickup power in a secondary side. It can be compensated using the secondary compensation, series compensation, which is capacitor. Then we have a rectification unit, which is a rectifier AC to DC conversion to supply the DC magnitude to the load. So this is the basic electrical circuit for WPT system with a series compensation. This is all. This is the thing which we are going to work with. So for this system, first and deriving the simplified equivalent circuit with the SS combination. Here you can see this is the output of the inverter. Output of the inverter is an AC fluctuating high frequency pulse is given to the magnetic coupling unit with through the primary compensation, series compensation CP. Then VAB is the output of the inverter. Then this is the internal resistance of the primary coil. Then the primary coil LP. Likewise, we have some imaginary term due to electromagnetic parameters. Then in a secondary side, we have LS, which is a secondary coil inductance, secondary coil resistance, then a series capacitor in the secondary side, then a load resistance. So this is the equivalent circuit model of the SS combination for WPT system. So by solving this equation, we got the parameter for calculating the ranges. So first we'll start with the load to the source. So from a load, we can take RL. RL we got 8 by 5 into RL. Okay, how we can calculate RL? RL is unknown, which is an AC resistance of the AC equivalent resistance of the load. So R0 is the DC resistance of the load. It can be calculated using the V0 by P. V0 by P is nothing but our output voltage to the output power. We can get the DC resistance, equivalent DC resistance. For that, we can make equivalent AC resistance. So by this, we can come for secondary inductance, which is LS. LS can be calculated with this formula, which is QS is nothing but a quality factor of the secondary coil, which we'll assume if we can see this in a calculation. Then RL is nothing but our load resistance, AC resistance. With that we can we have omega naught. Omega naught is nothing but resonant frequency. Our frequency which we are working with is 85 kilohertz. It can be converted to the then the IS is nothing but the secondary current. So secondary current can be calculated with the secondary voltage and the resistance parameter. Then the voltage across the secondary coil using this equation. Then the mutual inductance parameter is derived using these parameters, which is secondary current and secondary primary current with respect to load resistance and the resonant frequency. So we can achieve maximum power transfer in a wireless region at maximum resonant condition. So LP is not LP is the primary inductance calculated using this parameter from the M, LS, then K. K is nothing but a coupling factor. Then current across the primary coil. Primary coil current is IPRMS using this power input and voltage of the primary primary. Then the VPRMS nothing but our inverter output. So these are the electromagnetic coupling parameters for design. But we have compensation parameters CP and CS. CP and CS can be calculated using this equation with the help of LP, LS, and omega naught, which we know already. So this is for series combination for which can be preferred for static power transfer system. For we also have some other combinations like series parallel series that also we can try with this simulation. Then design specifications for our system, which I prefer, is 3.3 kilowatt system. We know that our standard will support for 85% of efficiency. So as per that, we have calculated the ratings with respect to the input and output. Here, there are some assumptions we have to make for the calculation. The assumption of that QS quality factor of the coil, secondary coil, which I have taken is 4. The reason is that generally you have to select the quality factor between 2 to 10. If we go for a higher QS value, it will make system tuning is difficult. When I go to lower value, it will make our system more harmonic for power quality issues. So in order to select an optimal value, we can select a 4 or 5 in that way. I have taken 4. So with the help of this QS, I can calculate the coupling constant Kc. So coupling constant is calculated using this Kc. With this coupling factor output, then calculated value, I can assume our K taken, which must be less than Kc. So this is a Kc. Kc is nothing but the critical constant. K I have taken is like coupling constant. So then IPRMS. We can calculate the IPRMS using the input power and the primary voltage. Then comes to secondary RMS using this formula. I can calculate the VSRMS, ISRMS using this equation. Then ILRMS on the load resistance, AC and DC resistance using these formulas. So IPRMS from this equation and LP, LS, M using these things. Then with the help of compensatory equation, I have solved CP and CS, which we saw here. These are the formulas that we derived here. So with that, I have got parameters for a 3.3 kilowatt system. So we saw our system design with the SS combination for compensation. There are other set of combinations we can go with series parallel series, parallel combination for static power transfer. For dynamic system, it's better to go with the LCL series combination. With addition to these all things, we have some hybrid combinations which I discussed in yesterday's sessions. So how we have to select our compensation network architecture. That is one of the important parameters. This compensation basically deals with whether CC or SS or series parallel or parallel series or parallel. It totally depends on the load. Depends on the load and the coupling factor of the magnetic coupling. So when there is some minor misalignment in a coupling region between a transmitter and receiver coil, it undergoes some misalignment issue. This can be addressed. It can be addressed, or it can enhance the power transfer using our compensation network by balancing the resonance. So then we have to take a rating of our inverter output and current rating. It can also support our flux linkages. Uh, this is how the compensation network architecture is selected. Then these are the parameters that we have to consider when selecting the compensation network. So then our system, we have designed, we have discussed about the magnetic coupling. Then we designed about, we have discussed about the SS compensation topology. Then we have primary power modulator unit, which is our inverter unit. So I said you before, we have a DC magnitude as an input. Then we need a high frequency AC power at the output. So this can be possible with a high frequency phase shifted full bridge inverter. So that is what we are going to discuss in the next slide. So here we all know about we all know about full bridge inverter, which is H-bridge inverter in a basic studies. So here we are going for phase shifted full bridge inverter. The reason is that we are working with high frequency, which is not in a normal range, which is about 85 kilohertz, which is range in the range in between the 79 to 90 kilohertz range. It's a big frequency. For this, selecting a switcher is a complicated one. Also, due to increasing frequency level, our our switch will go with thermal losses. So if I go with the basic H-bridge topology, not with a phase shifted operation, our switch will undergo some hard switching. So it will generate some thermal breakdown to the switches. So in order to these all issues, we are preparing for phase shifted full bridge operation. Okay. About this H bridge, there are two conditions to while designing. Okay. While designing a H bridge control pulse, we have to follow two steps. One is that two switches should not on at a time in the same leg. Another one is two switches should be on diagonally to ensure the continuous current conduction across the load. So this is the basic thing that we have to consider. By considering this, phase shifted gate pulse signal delay is included to support the system for soft switching operation by ensuring the this is a kind of phase shifting is a kind of zero voltage switching mechanism. So it can ensure our system is working in a safe mode. Also, it overcome the drawback of the hard switching. So this is what the phase shifted full bridge inverter works. So here I have discussed some modes of operation, how the switch will work. It will follow the two conditions where two switches should not get on in the same leg at a time, but two switches should on diagonally to close the circuit. So here you can see two switches is not getting on in any mode for any time period, but two switches are getting on at diagonally or to close the circuit, close the load across the circuit. So for that, the generated pulse will be in this form, which has the normal positive cycle and the negative cycle. Here you can see we have supplying our DC magnitude to the positive cycle and to the negative cycle. By this, we can control with a delay unit. By introducing some delay in the pulse, we can create the unit. Phase control, this is a kind of phase control, phase shifted control technique. It will give us output in this form in the blue color, which is nothing but on our voltage waveform, and yellow color is current waveform across the voltage. So this is what the output of our phase shifter inverter. So as of now, we discussed about primary unit and magnetic coupling unit. Then we are in a stage of a secondary receiver demodulating unit, which will receive the pickup power and it will rectify to the DC. Then DC-DC chopper is to enhance the efficiency to charge the battery. So this is our secondary unit. So these all about the WPT system. How we can measure the efficiency of the WPT system. Efficiency of the WPT system is measured using that mostly it is DC-DC efficiency. It's depend upon the input source and output drive. So it has three different stages of power conversion with the primary side, the secondary side, and the intermediate side. By comparing these all, we can determine the source to the load to determine the output efficiency of the system. So this is how the WPT efficiency is determined. Okay, we'll get into the MATLAB simulate model. So here we designed a system for 3.3 kilowatt system. Here I have taken several blocks. I said that we have three different blocks, which is primary unit and intermediate wireless coupling unit and secondary unit. Primary unit, here I have taken a supply from a grid. Then it is rectified to the DC magnitude with the help of DC link and supplying the DC power to the high frequency inverter. This is our high frequency inverter. Then this high frequency inverter is supplied to the transmitter coil through our primary compensator. So this is the primary unit. So this primary unit has high frequency inverter which can be controlled using this pulse generator. So these are the calibration input output measurement units. So this intermediate unit, after the pick up the intermediate unit, have the secondary coil. Here it is. So this primary and secondary coil are not connected mechanically. Both are isolated, but it is coupled magnetically. So this I have taken. Here we have secondary compensation unit. The secondary, through this secondary of compensation unit, we are supplying the power to the rectifier unit, which will charge the battery. This is how the system is designed using the Simulink model. For designing this system, we have to measure this. We have to measure self-inductance of L1 and L2, which is transmitter inductance or primary inductance from the ANSYS Maxwell. Also, we need to know about mutual inductance for a particular range of coupling. So for various range of coupling, let me get into the MATLAB. So this is our intermediate wireless coupling block diagram, which is a primary transmitter coil L1 and secondary receiver coil L2. Here I can feed the inductance value and the resistance value of the L1 and the inductance and resistance value of the L2. With respect to the alignment which I measured in the ANSYS Maxwell, I can feed that data here for various coupling ranges in the mutual inductance. So for various coupling ranges, I can change this value. Then I can analyze the power transfer efficiency between these and these. So previously I have simulated for this system. Let me show you this. Okay. Here I have a primary and how the power is getting transferred signal. I can show you. So this is the transmitter side voltage and transmitter side current. This is the receiver side voltage and receiver side current. So this is the power transfer happen in between these two isolated coils. So this we can analyze using this MATLAB. This is one part of which determines the wireless power transfer efficiency of the system. So sorry. So this is the simulation which I have shown here. This is a block which I have taken. This is a block which I have taken to simulate the intermediate wireless region. The remaining things and all, I think might be familiar with switches. So this is a special thing which I used here for making a block which is already available in MATLAB. With that, we are transmitting the power in a wireless region. Then the power is transferred to the high frequency AC to DC converter, which is our rectifier. This rectifier will supply the received power to the battery. So this is about our entire WPT system simulated in MATLAB. So let me tell you how I have taken the parameter. I think you all know about Simulink. We used to take in a library browser. In a library browser, these are the parameters which I have taken as normal parameters used to have in a lab generally. Here the wireless parameter is a transformer, high frequency transformer, which I have taken from the mutual inductance. With this mutual inductance, I have selected only the two coils. Let me show you. Here I have mutual inductance parameters. These mutual inductance parameters have 3 coils generally. By deselecting this, I have taken the L1 and L2 parameter, then mutual inductance. So with this, I have taken these parameters. Then this is how I did. So this is the procedure for it. Then selecting a battery. Battery we can take on a library. There are many types of batteries available. Then we have to select the charging and discharging parameters. So by that, I have obtained the output of the simulation. Let me go to the simulation. Okay, this is our simulation, which I have simulated from an AC source. So AC source power is supplied to the rectifier, which will convert the AC supply to the low frequency AC supply to the DC magnitude. Then it is given to the DC links. Then the high frequency inverter. High frequency inverter consists of 4 switches with a control pulse, which we can supply a high frequency pulse at the phase delay. Then I have a intermediate unit through our compensation capacitor in a primary and the secondary side. This is our transmitter coil, receiver coil, then secondary compensation, then rectifier unit, then battery. So let me show you the power which I supplied. Here is this is the input supply I have supplied to the system. Then this is the wireless power transfer. This is the wireless power transfer magnitude, which I can see here. So primary and secondary, those are the things. Then finally in a receiver unit, I have supplied the wireless power to the receiver. It is fed to the battery, and the battery charging performance can be analyzed using. So this is how we simulated in the MATLAB. So procedure are given in a step-by-step procedure. I have given in a slide, which I will share you. So So as a output, we are going to analyze the two varieties of efficiency. One is power transfer efficiency, and another one is electromagnetic coupling efficiency. So electromagnetic coupling efficiency can be calculated using in between the primary transmitted voltage and current and the secondary transmitted voltage and current. So overall efficiency of the system is calculated between the input supplied by the supplied to the inverter and the output of which is charged to the battery. So this is for 3.3 kilowatt system. Then we have simulated for again a 5 kilowatt system. So this is for the 700 watts. Likewise, we can go for a different power rating and we can simulate wireless power transfer system. So also another one block I said, which is script. We can simulate our equations in a script. In a script analysis, I have taken mutual inductance, which is K is equal to m root into L1 L2. This I have simulated using the coding, which is K1 and L1 L2 and M. K is nothing but a coupling factor, and L1 L2 is nothing but our inductance parameter. M2 is nothing but mutual inductance. So here I have written a coding to plot a coupling factor versus mutual inductance. So with that, I have coded to see the plot. So this will help me to analyze the factor between the mutual inductance and coupling factor using a MATLAB script. Also, we can use our own equations to solve in a MATLAB script. So here in a side, we have simulated for efficiency for a recoil system. Here program is written, then we can simulate, then we can take a response. So this is how the MATLAB will use us to analyze the wireless power transfer system using models. So also we can use our MATLAB tool for making real-time pulse generation using control pulses in our MATLAB. Then we can interface with real-time units. Then you can generate the output pulse to interface into hardware. So this is about the MATLAB use. Thank you all. Any questions you can ask? Sir, any questions you can ask?
Dear participants, kindly ask your doubts. Rahul sir?
Yes, sir.
New question is there, but it is about the previous. In ANSYS Maxwell software, what is the difference between selecting and not selecting enable iterative solver in optimetric setup? This may change the accuracy of result.
This is a question from ANSYS Maxwell. In ANSYS Maxwell software, what is the difference between selecting and not selecting enable iterative solver? Okay, if you are not selecting the iterative solver, our system will not go for n number of iterations. While enabling the iterative solver, we used to have the number of iterations that we need to number of iteration that our code, which is our simulation, how to follow. It's not, if it is not given, our error percentage will be increased. Any other questions? Participants, feedback link is posted in the chat box. You can fill the feedback. If you have any questions, you can ask me. Or else you can directly interact with me.
Thank you, Rahul sir. Participants kindly fill the feedback link that is posted in the chat box.
Thank you, sir. Thank you for the opportunity. So I thank all the participants for passionate listening.